let me start from first slide. So we are talking about the, in this chapter we are going to talk about the kinematic configuration and the motion model. First of all, we talk about the velocity-based motion model, because when you have a robot, that robot, you cannot read the odometry commands, as I a little bit explained already. And for example, you don't have wheeled robot anymore. Your robot is flying. Or you have a humanoid robot. That humanoid robot is, for any reason, the calculation of the odometry from walk engine is very inaccurate in the case that it can be possible. Then we can read the velocity-based motion model, and we will see how to formalize it, how to calculate it. Then we talk about the standard odometry-based motion model of mobile robot kinematics, and already you've seen the base structure, but we want to bring it in the form of probability in this chapter today. So why we are talking about these? Because we are going to feed these into the base filter that we've seen. So the UT that we've written there, simply motion command, we want to really bring it from really robot and feed it to the algorithm that we've had. At the beginning, base filter, later we go to Kalman filter, extended Kalman filter, etc. So what is the kinematic configuration? We say it is the calculus describing of the effect of control actions on the robot, or the configuration of the robot. And the common configuration of the mobile robots is 6 variables. That these 6 variables can show as the external coordinate system, x, y, z, and the rule pitch yaw, that where the angle of the robot is, Cartesian coordinates, and 3 Euler angles that we can show x, y, theta also as alpha, beta, gamma. Then if we simplify the problem for now, and we say, okay, calculating in 3D and all those and presenting them is a little bit complex, let's talk about 2D environment. And if we have 2D, we have robot pose that we mostly assuming and talking about. Then we have x, y, theta. As the always I refer to the robot pose and explain like x, y, theta for simplicity in 2D. But of course, if you have drone, then you most probably need to calculate and estimate all in 3D. Like the pose is not like robot is like looking with this, because it can be in any direction. And in mapping, we talked a little bit about it. So for kinematic configuration, what we have, the essential rule that we have state transition probability, that the probability says probability of xt given by xt minus 1 and motion command. So for now, you should clearly understand it. So from previous pose, we run motion command, and we get the new pose in form of probability. And this is essential in base filter that we've seen, and we are using it in the calculation that we have in previous slide. And of course, if you want to say, okay, what about the observation, how it looks like? It looks like this here. Probability of the observation given by xt. Here, we don't have motion command anymore, because robot just observes. Robot observation comes from the new state that robot it is. New state, I mean the current state. Here is coming from previous one, but observation comes from the same state that it is happening at the same t. So what about robot dynamics? Here we talked about kinematics. What about robot dynamics? It is still largely open and is not solved completely yet. And if we want to bring the dynamics indication, there are some approaches, and if you are interested in, think about it and see how we can update these to also include robot dynamics. So coordinate system, we can show the robot position like this, robot pose like this, that this is the robot. This is the orientation of the robot, where it is looking like. That also we call it as bearing and heading direction. In different books and in different references can be different. Sometimes you may see bearing, sometimes see the orientation or heading direction. I sometimes also refer as angle of the heading of the robot. And here, x, y, of course, is clear, and we have theta. That theta is the related to direction of the x as initial 0. So we can assume that if the robot is heading here, like heading to the x-axis, and theta indicates how much rotation we've had based on that 0 assumptions. Is it clear, everything here? Okay. So we say motion model plays role of the state transition model in the mobile robots. What is the state transition? Also, we are talking about reinforcement learning. If you have the same thing from one state moving to next state, the probability form of the, what is the probability from one state to move to the next state, that here comes from where a motion command that we are running. If you are clever, you can connect these two. If you, some of you, I think most of you have the reinforcement learning class too, you can see that there we have observation, and this can go also fit to the algorithms over there, maybe too, and of course then that can be nice. But of course, actually there we are trying to learn this one, and reinforcement learning tries to learn it. So what note I put it here, xt and xt-1 are both robot poses and not just the x coordinate. So I think this is clear so far. Formally, this model describes the posterior distribution over kinematics. In also books you will see that it is called as posterior distribution over kinematics. So when you face with this posterior distribution, it means the same term, that is probability of xt given by previous xt and the ut, the control command that we run to come to xt. And the distribution, this probability, if we want to visualize, you can see that, okay, robot moves from here to here, straight line, then the distribution can be look like something this. Why it is like distribution like this? Because like here we can say, okay, moving a straight line for the robot was more accurate, the rotation was less accurate, so that distribution like this. This is not limited to straight line. Robot can move any trajectory, it can run any trajectory on the path, and also different passes. Then again we can have the posterior distribution over kinematics that you can see, or similarly the same probability distribution. I want to clarify for you, when we are talking about localization, when I'm moving from there to here, it is like I'm going to predict the probability where the robot is, because I cannot say exact xy. I want to say somewhere around this circle, and this circle can be distribution like these shapes here. That says, okay, more likely robot is here, but maybe here, maybe here, maybe here. Less likely here in this distribution. But if it was Gaussian, then everywhere it was like the same probability in one circular on the xy. So what about the velocity-based and odometry-based models? We say in practice, odometry models tend to be more accurate than velocity. Why? What do you think? Odometry tend to be more accurate than velocity model. Why? Not really. Yeah, I know, but exact answer. So now you need to load what was the odometry and load what was the velocity model. Then why do you think that odometry model is more accurate than velocity based models? That we are going to break all of two of these down today in mass form. No idea? That's simple. No. Yeah?
The odometry models can decide which is the axis, x and y, something like that.
How?
So from the distance of the odometry sensor,
Okay.
and then the velocity, just for moving the velocity equally, then know what's the distance.
Yeah, exactly. So actually in odometry model we have sensors and we can read it. Your robot has wheels, moves, you can read it, right? How much the distance robot is moved. But in velocity what you have? It's just velocity of the what the robot is moving. You cannot read any single move. And based on that, you need to kind of estimate it. Kind of say, okay, if my speed is this, my angle, robot's angle is this, and moving in this direction, that we will see if it's rotating also, how we can calculate it. But here you can read it. I can read my wheels. If it's on humanoid robot walking, you can read it, step sizes, and accumulate what are the step sizes, and finally what was the rotation and where I ended. Because of that, this is more accurate, but in most of applications we don't have access to this, and we have to use it. And in advanced SLAM algorithms, both can be used, and this one also is the velocity model is also very common to be engaged. For example, we will see later on one advanced one, the basic concepts of the OrbSLAM, so that there you will see that also we can have velocity models as input of the algorithm. Also, one important point that in Kalman filter also we will consider velocity models as input because it's easier to plug in the equation. So most of the conventional robots do not execute velocity commands. Also, this is another reason. And also odometry is only available post the fact. It means that you should run whole procedure, then you can calculate it. This is also critical. But in velocity, you can say, okay, if my velocity is this, speed is this, you can kind of, before running, you can estimate it. That's also kind of tricky and useful point that makes it more kind of interesting to consider as at least one element of the prediction step. So usually the odometry models are applied for estimation, whereas velocity models used for probabilistic motion planning mostly, but they can also be used in both of them. But this is kind of general thing that we can consider. So first of all, now we want to talk about the velocity motion model. We say it assumes that we can control robot through two velocities, a rotational and a translational velocity. So you remember we studied about the rotation and translation. And translation means that a point in 3D or 2D we want to directly move wherever we want move. Rotation means that we want to rotate it simply. So the translational velocity at time t, we can show it by vt, and the rotational velocity we will show it with wt. That can be shown as this term over here. The control command ut is equal to vt and wt, translational and rotational. So now think the base filter. We were talking about the ut. ut equal to the door is like the push, do nothing. So in previous slide chapter we discussed like that. Here we want to replace it with velocity motion model, that the motion model ut that we have in the base filter algorithm, that small term there can be shown by the translational and rotational movements of the robot in the environment. We can define some rules for it also. We can say, for example, if the WT rotation is greater than 1, rotate to the left. Is it smaller, rotate to the right. And if it's 0, do now rotations. For forward, the same. VT is greater than 1, move forward. And 0 is do nothing. And negative values move backward. Also, this is very common in this form to be used in implementation of the humanoid robot walk engine. We usually, I want to recap there, like your robot is walking, you can apply the velocity of moving forward and rotation by control commands. If you are familiar, some of you are familiar with humanoid robots, but later on you will study, you will work with advanced robots, you will see that even in drone, similar to drone. So you can adjust the control commands, motion commands as velocity of moving forward, how much move forward and how much rotate. And combination of those can give you the final endpoint that you want to reach, whatever it is. Clear? So, okay. Now, we say, okay, a noise-free robot moving with constant velocity v and w, if you want to show, can be generally look like this, that when the bearing of robot is like this, robot, based on the v and w that we are giving, can move around one circle. And this circle will be very helpful for us if we can find the center and where it is. We can use that to predict where the robot is moving to. What does it mean? It means that if we have a v and w, the velocity of the moving forward, translation, and rotation, 2 parameters, 2 values for those. Then, based on those 2 values, I need to somehow try to find where this circle is, find the circle, and where circle is, and estimate where the robot is moving, and say, okay, robot will be here, for example, will be here, will be there, will be here. Clear? Based on 2 velocities. That its radius can be shown as this, but we will calculate it. So in this here, just simply, if we know xy, and the radius can be r, but we will see that in next slides how much magically can calculate it, and we talk about it. So what we need to do at the beginning, let's assume that from xt minus 1, that robot is in x, y, theta as initial pose. We want to have constant velocity vw for some time at delta t time, robot moves. We want to find out where the xt robot is based on this one, the velocity given, and delta t time given. The main objective is, okay, let's say find out where robot can be in xt. To do that, as I mentioned, we need to find the center of circle. What's the center of circle? The circle that this v and w are causing. The circle that this, like, if we have robot here, based on the V and W, robot can like go this arc. Robot can go, let me draw this arc, or can go this arc. What what is the idea? The idea is if we can say, okay, this is a circle because it is circular movement on delta t time. Then if we find the center, we can mathematically calculate it based on the delta t that we have. Where it is, estimate it. For this circle, we have bigger circle. Then we should find this point, the center, critical point. And based on that, then based on the delta t that we have, we can say where the robot is supposed to be, based on the V and W translational and rotational values that we have for our velocity-based motion model. So what we do for xc and yc, mathematically we can calculate it, as you can see here, with sine and cosine rules, that xc is equal to the x, where the pose is, the x, and based on the subtracting it with the velocity over the translational over rotational times the sine of theta, we can calculate it. Based on the sine of theta and the position of that, we can calculate the xc. In math, you've done that many times. Even if you have computer graphics, you need to like construct 3D circles. You can use this term over here to calculate where the prime, draw the 3D points on the mesh or 2D environment by calculation of the xc, finding the center and drawing the points then later. Then for the y, we can take it with cosine. Y added by this term over cosine. That we determine xc and yc by this term from math, simply. Then, after delta t time of motion, our idea, as I mentioned, is to find out where the x prime, y prime, and theta prime is on xt. How we can do that? We can write this term over here, that x prime, y prime, theta prime is equal to this term over here, xc added by what we've shown, how to calculate the center and this term, and yc calculating this velocity over cosine, and the theta added by w delta t. So what does it mean? It means that we have new pose of robot is equal to the old pose x, y, theta added by the calculation of the translation on the xy and the rotation. Again, xc and yc came from this term over here, that here xc and yc just replaced by those, and we plug it in the term over there, so that we can calculate the if we have the xy theta, based on the xy theta and based on the w and v velocities, two velocities, we can calculate the x prime, y prime, theta prime by using this term over there. And the idea was, first we found the center, then we calculate where the robot is going. So now, so I also included some explanation. This comes from trigonometry, geometry that after delta time, the robot progresses v time delta t along the circle, resulting heading on w times delta t. That is delta t. So this delta t, this calculation over here, just shows how much robot moves on the circle, how many times robot moves on the circle, and calculates its time based on the center, and we can have it over there. Then we say at the same time, x and y coordinates given by the intersection of the circle about x, c, y, c, based on the center that we have, and the ray starting from x, c, y, c, and this is like a line that we can have like this line. So now, one thing is remaining, one important element is that this equation, if you write it simply, just plug the values over there based on the previous poles and the things, will work. But what's the problem? The problem is that, okay, we say the control commands are not accurate. Robot cannot run it accurately most of the time. We have error over there. But here, everything is exact. So I said, I have the robot pose. And I said, I have VW, the velocities, rotational, translational. And I show you exact calculation that how we can calculate where the robot is. But what about the error now? So then exactly we know where the robot is in the velocity motion model, right? If we implement. So due to that, we need to also apply error on this term here. That error, as it is also well explained in the book that you can study. So, and also we discussed multiple times, robot starts from this bearing, rotates to go there at the velocity, then error can be looked like this, can be looked like this. And if we're sampling from those errors, because these are infinity number of points in distribution, in probability distribution form, we can also sampling those that we can have error like that. And the different noises can be different over there. Now we need to, the idea is find somehow in the calculation that we have add also the error noise. In order to add in the noise, let's see what we can do. First of all, we say, okay, this VW we had already, the velocity of the translational and rotational, some values. Now we want to add noise. We can say, okay, now we can write v hat and w hat, new variables, like based on VW, we have new variables v hat, w hat. That also includes the error. That also includes the noise. Just by adding some noise, simply. For v, we can add this noise over there. That is epsilon alpha 1 and epsilon alpha 2 based on the v and w, based on the translational and rotational error that we have. So epsilon, usually we use it in everywhere. Usually we use it with a small amount of value of error, for example. Then we have the error for what? Error for translational. That is can be different also with the error for the rotational movement of the robot. That we can add it on the translational, and we can add it for rotational. And in the rotational error, again, we have both the translational and rotational error. It means that although your robot also just only rotating, maybe it is moving also in some direction. Not only error is on the rotation, but also error is on some forward direction too, that we can add. So now, what are these parameters? Where does these can come from? You answered? How, where we can find out these parameters over here? This V and W is clear. the control commands. We say robot move forward with velocity of the translation of 0. For example 2. Let's say, let me a little bit clarify this here. Like, let's say you have a robot. What kind of robot maybe draw? This is drone, for example. That is flying. Okay. Then you can have V and W. So let's say it's on the range of the V is on the range of the -1 to 1. Maybe use it with column. And again, W is -1 to 1. 1 is maximum speed. So if we put 1 here, is the maximum speed of moving forward. If it's -1, maximum speed of moving backward. 0 is like being stable. And W based on the rotation to the left and right with maximum or minimum. We have these values that already we know. We send to the robot to run. And based on that, we saw that how we can calculate on this circle where the robot is finally. And now we are adding the error. And adding error on V and W, adding error over here and over here. And where those coming from? Yeah? Again, we need to test it. Simply, your robot, you test your robot from here, you run motion command move forward. If it's completely straight, that's nice. But it ends up a little bit in the right or a little bit in the left, you add the error. You adjust the parameter here for moving forward. What is the error of the straight movement or rotation? So what does it mean, straight movement and rotation? Your robot may go and head like this, like a little bit moving forward. Let me example again. So your robot may move and end up here. That is the error that you have on the straight forward movement. And your robot may have error on the rotation, end up from there, come here, but end up like this. And that's the error that you have on the rotation on just control command that you're saying, okay, my robot goes straight. And for the rotation, again, if you have some rotation, you may have the error for moving straight and rotation again that you find it on your robot and plug it over here. Any question? So now let's say, okay, common choices for how we can show those errors, like how you may think, okay, I know that error or some value. How to add it to my equation is like you can use the probability density function with some variance b that shows how much error you have. If we want to add the error to the system in probability form, that's very simple. You can use, for example, normal distribution with zero mean. Zero means that is like, and we don't care about the mean, but the variance, how much is bigger, my error is bigger. How much is smaller, shrinks, my error is shrinking. And the error that we are talking about is in form of the like the epsilon b, that the epsilon that we discussed here, the epsilon. If we consider all these term as b, we can plug it at, for example, if our distribution is normal in normal form, and increase the being unlikely where we are supposing to run. Another way is triangular distribution, that you can see both of equations, how we can calculate it, this term over here, this term over there, and density of the distribution function is shown by zero mean and variance b. So, okay, later. I have some implementation examples that I will show you soon for those, because some of you have some small problems over here. Now, The better model of the actual pose, xt equal to x prime y prime theta prime, after running the motion command v and w, at the time xt minus 1 on the xt and wt can be this term over here, but what we studied, simply everything is same. We just change the v and w to v hat and vw. That includes noise too. Same equation, same term that we calculated for the prediction of where the robot is moving on the based on the motion commands of rotation and translation. We just, the rotation and translation also this time include the error. How? Here. Here. We show. V hat W hat is equal to VW that we have added by error. And error can look like this, and we have finally that term over. Clear? One thing is remaining, and what is it? The thing that is remaining is final orientation. If we want to generalize the solution that we have for velocity motion model, it means that, okay, now I exemplified this here. Robot bearing is looking like this, and we have the VW, some constant values, some values. Then robot, let's say, moves this green line. And if we, based on delta t that we have, if robot ends up here, what will be the bearing based on calculation that I have? The bearing will be this, right? So robot moves from here and comes and ends here, and bearing is like this. But what if I want to generalize to show other bearings? If I want to use the same term to show if the robot is moving, but bearing is not there, is here, or is here, or whatever it is. So to generalizing to representing that one, I can add one more parameter that is called gamma delta t to the calculation of the orientation that I had. So here we calculated the x prime. Here we calculated the y prime, the position. Here we added the theta, the orientation or the bearing of robot with this term over here. But now if you want to add that, we just simply add gamma delta t. That this gamma delta t represents the final rotation of the robot that we may have. And of course, that final rotation again may have error. And that error can be also included by epsilon alpha 5 and alpha 6. We had alpha 1, alpha 2 for these two, alpha 3, alpha 4 for the second one, and now for gamma, alpha 5 and alpha 6, because they are different values that we can adjust for the final error that we have on the rotation of the robot. And final pose. And that's since it is included the noise too, I've written also in the book it's written as gamma hat. If it was gamma, then it had no error, just the rotation. And that rotation also can be depending on the time that amount of time that we apply the additional rotation. Okay, so any question? I'm losing my remote. Now we want to see the algorithm of what we studied. Calculations of the algorithm for computing probability of the xt given by previous x and motion command. So the pose of robot given by previous pose and motion command that we run. based on the velocity information that's given, and the velocity information that's given for this position, and the velocity of the translational and rotational movement during delta t. So here we just want to bring it and show it in probability form, that how we can show the probability of the, if robot moves from initial pose to x prime, y prime with these parameters, then how we can calculate. The general algorithm will look like this. First of all, I define the some nodes, and I explain what are the nodes there. Then I break it down a little bit and explain what's happening over there. So first of all, we say xt minus 1 is the vector, the pose of the robot. Xt is again the vector, new pose of the robot, x prime, y prime, theta prime. From here, robot moves to there. Ut is the velocity vector, v and w, that we indicated clearly. The probability A of B, we will have a function, probability of A of B, that is here. And also I will open it how it can work. I will show it. It computes the probability of its argument A with a zero-centered distribution variance B. So the distribution zero-centered and variance B, how much the error is, and it brings it to the form of probability. Then we say control can be computed during delta t constant time. There is a reason that I put it here, because we say, okay, when robot is moving, of course, speed can change too, right? And here we are not talking about the change of the speed. We're saying if the robot is moving and we are predicting over here, the speed is constant. Because of that, delta t is constant. If that moves, we need to also consider that one. If changed, I mean. We say, okay, the v and w are constant during delta t. They are not changing. Because if they're changing, it ruins everything. You need to include it. Or you can break it down to small time steps, so that you can calculate between those time steps that the speed is not changing, and kind of discrete for it. And parameters alpha 1 and alpha 6 are the robot-specific motion error parameters that we explained exactly. 4 at the beginning we explained, and 2 later on the final rotation that were indicated are alphas. Now let's break it down. First of all, we want to find the center of circle. So what is the center of circle? When I'm referring circle, I mean this circle. And I want to find this center here. Or here. We want to find it out. How we can find it out in practice? So we can have these 3 terms here, center of circle. That this center of circle can be shown as x star and y star. Finally, we want to, here written xc, yc is the same, x star and y star. So we say for the robot that move from this point to x prime, y prime, we want to find the x star and y star. We don't have theta anymore, of course, because we don't care about the angle here. We just want to find 2 points. In order to do that, we can write this term. So I'm explaining what's happening here. For the center of circle, we can calculate in general in mass x star y star is equal to xy of the point that we have, and the lambda sine theta and lambda cosine theta that is equal to another term here, and this first term means that circle center, this circle center is orthogonal to the initial heading of direction of the robot that we want to calculate later. So that this orthogonal means this minus and positive. Because of that, it is orthogonal. And why that's happening, that comes from mass, how we can find it. I'm not going to prove it exactly. And based on that, what we want to do, we basically want to calculate the halfway of the calculation. And adding halfway means that if we have a line here for this circle, we are talking about finding the center circle, and this is in the middle halfway, right? Because of that, we can write this term is equal to this one over there. But where the mu is coming and how, so this division by 2 is x added by x prime divided by 2, it's simple. And y same, we just add it and divide it by 2 to find the center. But how the mu is coming for adding this term over there, it comes from here, and this is a unique solution to find it out. And it is already proposed to you in math. So this mu can be calculated by this term here. I'm not going to prove. If you are interested in, go study why that's cosine, this term like 1 over 2, why this is happening over there. And finally, if we plug it back into mu, then we have this big term over there for calculating the center of circle. And if we want to write it in form of code, we can write it like this. Finding the mu based on the parameters that we have, x, y, x prime, y prime, and the theta. First initial, this theta, initial bearing of the robot. Then based on the calculation of mu, then we can plug the same term over there, this one, put it here and calculate it. We can get the x star and y star as center of circle. So if you find the center of circle, we went most of the path here. Then finding the other things will be easier. How? Let's go step by step. First of all, we need to find the radius. After finding here, you can find the radius. Here we represent it as r. That what is it? It is simple Euclidean distance. Distance between, differences between x and x star, center of circle, and the x, the point that robot is, and the differences between y's, and if you get the square root, it becomes Euclidean distance, and this gives you a value that shows a distance, simply. Okay, clear? After that, what we need to do, we need to calculate now the amount of change of heading direction of the robot. So from here, the heading direction changed to there, right? This heading direction, how we can calculate it, but this line over there, that is arctangent 2 of the differences between the center and the y and x, the center of the circle and center of the where the robot poses, and arctangent 2 of these over there, like the differences between the primes ones and the previous one. The differences between this one and this one. For each one, find the arctangent 2 and find out the differences. Then you will have the change of the heading direction, how much it is changing. So for arctangent 2, we already seen, but arctangent 2, if you have like x, y, a point on the coordinate system, you want to find theta, you can write theta is equal to arctangent 2 of the y and x. So be careful, y and x. Then if you calculate arctangent 2 of y and x, you get this theta. And based on this, we can of course find out the first one and second one, and find the change, amount of change that we have. So this arctangent 2 also implemented in most of the programming languages, and it looks like this because we don't have arctangent 2 in math. So it can be written as arctangent 2 of y of x is equal to arctangent, if the x is greater than 0, this element is greater than 0, we use the arctangent of y divided by x. If it is smaller than 0, we use this term. if it's x equal to y and both of them are 0, we put 0 there, and if x is 0 and y is not 0, we just can sign off the y. So that's how we can calculate arctangent, and arctangent can be applied on this. Then we have finally delta theta. That delta theta represents the changing of the heading direction of the robot. Then now finally we can, not finally, but now we can calculate the velocity v hat and w hat from d distance and the delta w. The delta theta. Delta theta, we found it over there. So delta theta, we found it over here, the amount of change. And now we want to calculate the velocities, two velocities, how much are they based on this calculation over there. What we need to do, calculate that one over there with delta distance. So delta distance can be written as distance times delta theta. What does it mean? It means that the amount of movement that we've had, if we multiply this with delta t, the amount of change, then using that amount of movement and amount of change, if we multiply that, we can write our motion command. Our motion command is equal to v hat w hat equal to delta t transpose times delta distance and delta theta. This delta distance is this term over here. We place it, plug it here. Then if you time it on this, we can have this term over there. So this one times this one, if you plug it here, delta distance that comes from times of these two can be r star times delta theta over delta t. That gives us the translational velocity. And for rotational velocity, what we do here, again, delta t transpose times delta theta, that becomes delta theta over delta t. This gives us the orientation, the velocity of the rotation, actually. And angle of final rotation that we discussed, we needed to add, don't forget it, the gamma. The gamma can be written as the differences of the theta prime and theta, the differences of the rotation subtracted by w hat that we defined over there. Exactly, it just comes here. So then finally we calculate the rotation, and we can show them in form of probability. How? We can return probability of the differences of the v and v hat. So the command that I sent to, and the command, the velocity that we sent, and the velocity that we calculated all these efforts here, and the error, and represented in the form of a probability, this function here. This function gets the mean and variance. And mean and variance are like, we can this mean and variance. The differences and the error of v times the probability of the differences of for translation, for rotation, and for final rotation of the gamma. Then all these can give us the probability of the velocity motion model by calculation that we've shown. If I want to show the normal distribution function, how we can implement it, you just need to write algorithm, probability normal distribution A and B. A and B are coming here These ones, A and B. Then A and B can be, you can implement this code over there. If you have normal distribution, if you have triangular distribution, we can write this form over there, calculation of the return of this term or that one. Then that's it. A means the mean and B standard deviation, here of how each observation value can be changed over there. I also show how you can do that in form of probability. I've written a function for normal distribution, not using the library, that you can, for example, if you want to implement this over here, you can use this function, normal distribution function, to generate this, or just calculate the value without generating whole of it. This gets all x's as all the points and calculated each one by one. And here just calculates the final result, and I printed it. So for example here, to after calculation bring it and make it in form of probability. I show that because these are simple maths. You should not have any problem, but I see many students have finally problem of how bring it to form of probability, the values. This can come to form of probabilities like this, simply. Okay, I think I'm not going to continue odometry motion model because you can get exhausted, I'm sure. Because also we have lots of math here too, but that's very simple, the hardest one we went through. Okay, any question? This is also assignment for you, but you will have long time because you have already one. Just you need to code this, but you will have long time to do that. Why laughing? Yeah, I know. If you want to learn, you need to implement. Otherwise, you don't learn. You just go through the general example. I also have many implementations of these, but if you do that, you have to do that because there is a reason. Because all this is just UT, and that UT goes where? All that equation, we just calculated one so far. So this is Islam. Welcome to Islam environment. And for the observation, we have something similar that goes to, and based on the sensor that you have. If there is no way, you have like laser scanner, LiDAR, you have vision, you have whatever it has, it should be modeled to come into the what we are wanting to feed it into base filter and make it more complete later, then so that that can really work. And in industry, in real environment, and really you can make it use. And if you implement these small components, you just plug it together, then you have finally a big, very nice algorithm to be engaged in any problem that are state of the art now. So for now, I think that's it. We can finish the class. No need to, because we don't have break. Of course, I don't use those breaks, and I terminate classes earlier. Any question?
What's the difference between X star and X prime and A?
X star is the center of circle. Here, let me. This is the X star and Y star. No. Sorry, not that one. Here. X star and Y star, center of circle. XY is this one, and X prime and Y prime is this one.
So X star and Y star is the same as XC and YC.
Yeah. Any other questions? So you're running fancy algorithms. You're seeing on the YouTube that this is like very nice algorithm and it localizes very well. And our professor is not teaching that. So that comes from here. This is just UT that block. That goes finally, that makes it fancy algorithm. Otherwise, we can go directly download from GitHub and run it, and that's how it works very nice. I'm running Islam algorithm, changing some parameters, and I'm running Islam algorithm. So that's not how it works. This is how it works. And this one, of course, go to advanced algorithms. Like we talked about velocity motion model. We have very nice algorithm, Orbislam. And that uses the inertial, and that uses the velocity of the IMU to improve the monocular visual slam. And to increase that, this velocity motion model plugs into those advanced algorithms. Not only this will be useful for our all algorithms, Kalman filter, extended Kalman filter, particle, many algorithms that we are going to study, but also advanced algorithms are using it. Because of that, it is important, and I think I clarified everything like crystal. I think you just need to a little bit look at the mass and what is happening, what they are coming, and try to implement it to make it concrete for yourself. Any other question? Okay, good. So I dismiss the class. Thank you very much. See you next week. So today we are going to talk about the odometry motion model. What does it mean again? So in velocity motion model, we said that we just want to, since we cannot read any sensor, so we have the velocity parameters and robot is moving in the environment, and based on that, we wanna estimate or calculate where the robot is going and what is the prediction for input of the base filter. But here we say, okay, if we have odometry and we have sensors that we can read, and based on the robot that we have, then what we need to do. First of all, before entering into the topic, I need to clarify this for you guys that now we have two elements. Like imagine one wheeled robot that moves in the environment. What are the two elements? One is the sensor reading that we have. I call it as odometry. The one that we were talking all the time about was control commands. And control commands were like, you're saying, okay, move forward 1 meter, 10 meters, 5 meters, right? That's the control command that you send. And you're supposed to end up after, like when you say, okay, move forward, your robot's supposed to end at 5 meters. But, okay, this is useful information, right? This is our knowledge that based on that, in Islam, we can say, okay, we know that our robot was supposed to move 5 meters. We are expecting that robot is after 5 meters based on the control command that we are sending. On the other hand, second element that we have, odometry reading. That this odometry reading reads some values for us and says, okay, how much we moved. So we have two parameters that these two parameters are useful for us to consider, take into consideration. How? We will dive in soon. So we say it is also common to simply consider the odometry as a control signal, and the resulting model is a core of the many probabilistic robotics systems that we have. So, of course, if the amount of movement and sensor reading by odometry reading, if it's equal to the control command that we have, it's the idealistic and that's the best. Then we don't have error actually. But of course, robot sleeps, the wheels is sleeping, the error that is happening in the robot, then we don't have fixed coordinate transformation also, and physical world changes everything for us. If you want to have a quick recap, we already seen how to calculate this. So we said in simplest form of odometry. In simplest form. Let's consider just robot moves straight. So first of all, we say, okay, robot is in some pose. Then robot rotates, then moves forward, then rotates again. So with this presentation, we were able to talk about robot that moves in the environment anywhere. And we said that, okay, here we can find the alpha 1, here we can find the, with Euclidean distance, the distance that robot moved, and here we can find the alpha 2, how much final rotation has been done. Now, we want to pull all together and bring the odometry reading and control command reading and show it in probabilistic form of the error, how what is the probability of the error that we have based on the control commands and odometry reading. So consider this again, keep loaded in your mind, but here the name of variables are a little bit different, but the same concept, and the calculations, the same calculations, just the variable names are a little bit different. If you want to bring it in algorithmic mode, what we need as input, the pose, the control command, and the previous pose as input. And what we can do, we can, first of all, calculate the odometry reading. So what does it mean? It means that based on the parameters that my robot as odometry reading have, like robot rotates, moves, and rotates in the environment, then my sensors reading some values. And those values are showing with these hats, like Y prime hat, X hat. So these X's are the initial pose. Then robot moves, then we have the prime ones, and theta prime are also indicating the amount of rotation in the environment. First rotation and second rotation. So that I can calculate this one, delta rotation 1 over here, then second row here, this one, I can calculate it, and this final rotation I can calculate in third row. Very simple, exactly what we've studied. But as I mentioned to you, now we have odometry reading calculation, and we have 3 values for each one of these that they are indicating, okay, what was my sensor reading and how much robot moved. But we have another important element that I told you, and that is the motion commands parameters. And that motion command parameters are the parameters that I tell into the robot from here to go there. And based on that, I can do the same calculations, right? The same things can be calculated based on my control command, because I'm telling, okay, rotate 45 degrees, move 5 meters, and again rotate 30 degrees. Then based on that, I can calculate the same scenario for motion command. And after this, of course, I think it's very clear that how we can bring it to probabilistic form. So we simply need to use the same function that we had in previous example, the prob, so that I can calculate P1, P2, P3, three probabilities that indicate the differences between these 2 parameters that I have. These are with hats that you can see the difference, and here the difference, and there just the same alpha 1 to alpha 4, the amount of error that I can also add to the system based on the error that I know that will be applied on my control command to increase accuracy, I can consider. Not only the pure control command, of course, I know that plus my control command, I have another error. And that's very optimistic if I want to directly say, okay, my control motion parameters and control command is 100 accurate, directly bring it to the probability. So I also can add my error on the control command and say, okay, I tried already 100 times and I know robot error is like that, and add the parameters here. Then merge these together with the odometry reading over there, and finally merge all together and return the P1, P2, P3, that they are multiplied to each other, and one probability can show me where the robot, for example, what is the final error of the robot that is moving after running such a trajectory for me. So of course, for example, if robot has more error on moving forward, and if you go very far, the probability distribution over there will be increased. On contrast, it can be smaller on the here, if it's, for example, the error considered as Gaussian distribution, and we plot it as normal distribution. So now the question is, okay, let's say if robot moves on curve like this, how we can consider that, do you think? Because this is the simplest form of, well, very simple. We calculate everything like rotating, move forward, and rotate again. Now if we have like robot moves like curve, based on odometry reading, what we need to do? That's one discretization approach that we can do, but it still has error, because how much we make it is smaller, still we have error and we're losing. Like we have integral and we discretize it and we're losing something there. So same problem will happen here. Any other answer? I think it should be very clear now, based on last week and this week's study.
So instead of the transition model being a straight line, we can go in a circle.
Yeah, exactly. We can bring the parts that we studied last week about velocity motion model, and we saw how we can calculate on circle, and how we can find the center of circle. We said, okay, robot is here and moving, we can find the center of circle, and based on this we can estimate, okay, where the robot is with some calculations. We can do the same thing here, but we need to bring the parts that we need in those calculations to consider it inside here, instead of, for example, these 3 lines of the calculation. For example, for control command, motion parameter control commands, you say, okay, my Vx, if I consider Vx, Vy, V theta, that robot moves in the environment, this is like, if you consider control command instead of velocity, then where the robot ends, you need to reform the calculation in order to be able to do that. Yeah, question? Okay. Needs math work, needs you to engage how to formulate it, but you can also bring it into calculations, or also, as your friend mentioned, you can sacrifice some data and do some math work to also consider the circular movement of the robot. So Now I would like to talk a little bit about the humanoid robots because also that's very useful for you. For now, our all considerations were like based on real robots. I'm not going to show all calculations because this takes like 3 weeks of teaching minimum. Then because I need to explain all the details, but I want to give you a general concept. If you already work with humanoid robots, you're already familiar with, but let's see what's happening here. So I'm going to explain, okay, if you want to have odometry output from a humanoid robot, what does it mean? It means that, first of all, you have a robot in any configuration that it can be. And that robot has kinematic chain. Kinematic chain means how the arms and robots, legs and body connected to each other in simplest form. Then based on that, you basically have implementation of the control that can be like inverse kinematic or forward kinematic. What does it mean? It means that let's say, okay, I'm a humanoid robot and I want to control my arm. So if I want to grasp this object over here with my right arm, what I should do as programmer, so for each one of the joints that I have, I need to send some position so that my arm reach here, right? But isn't it too hard? Because in 3D workspace, even you don't know like what should be, how you can say what is the position of this joint and this joint to be there. Too many parameters. And if it's just one time, that's okay. You can find it for position of each joint or angle of each joint. But if you want to do lots of things, then that's very complex, right? Not only the arm, you have legs of robot, right, left, and everything. And sending exactly the position for each one is very difficult. Because of that, you can have some mass calculation that based on that mass calculation, you can in fact implement inverse kinematic. For example, one of the examples. There are many approaches also of the inverse kinematic. So, for example, if I want to briefly explain like analytic one. What happens, you write some equations so that you say, okay, I have the x, y, z of this object on 3D environment on my workspace. Then I want to have a function that if I consider my right arm's end effector, end point, and send where x, y, z I want to be, then that function calculates all values of these for me. I implement one time that. That's very complex. If you want to implement from zero yourself, you're going to suffer a lot, but that's worth a lot too. Because you one time implement it, the next time you say you call that function, okay, go to x, y, z. Then it calculates how angle of each joint should be to be there. And not only x, y, z, you can have rule pitch yaw. Rule pitch yaw of how should be the angle on the end effector, which is the heading direction of that the end effector to that object. So now we extend this knowledge to robot, humanoid robot. We have on same scenario on the leg. So for example, I want to say, okay, robot brings his foot or end effector, end point of the feet to the forward, like right foot to the forward, without z. So you can increase the x, and robot should be able to achieve this x. You increase the y, for example, you increase the z, then you can achieve any 3D coordinate with robot leg that is achievable for your kinematic chain that you have. Because, like, if I want to say, okay, nothing else is moving, right foot go x there, impossible, right? I have some limitations, like this is the end of the point that I can achieve. And then you can calculate it. So this is the meaning of the inverse kinematic. We have some functions for each independent, for example, arm and foot. Then you have some functions that can give you the answers. The second part is trajectory planning. Trajectory planning means that, okay, now I have it. I can have control of the each one of the end effectors, end points of my robot, legs and feet, legs and arms. So I want to say now how they should move to be able to walk in humanoid robot. So what do you think? What is your idea how it can be possible? Imagine a little bit. You have humanoid robots. So far we implemented everything and we got to the point that you have control of each one of these then. With for example, X, Y, Z rule PTR per each one of these 4 elements. Then how you can implement walk engine or trajectory for that walk engine. There are different ways. If you think, okay, I can say this is robot leg, then I can say, okay, this is X, Y, Z, then this is X, Y, Z, this is X, Y, Z, this is X, Y, Z. I can generate walk like that. But that's very difficult, right? If you want to do again manual. Same as what I explained here, that in analytical form we had it better form. Instead, what we can do, we can say, okay, we have, for example, sine and cosine, right? And what if my robot, for example, right foot, if you look at from side, like look at me like this, if robot right foot follows this sine, that's very interesting. So because I have inverse kinematic, I can send the position, and if I generate this part of sine, and robot foot follows this, then I'm generating this trajectory. And the other foot can be on cosine. For example, on movement like this. Just consider upper bound. And simply like with sine and cosine, just you can generate this. With simple function that your inverse kinematic follows this. But of course, it's not that easy. You need to do a lot of things on the center of mass. For example, if your robot like does this, then of course falls to the right. So you need to generate trajectories on like swing, then lots of additional parameters on the Z, and maybe you need to add 10 of these, combine 10 of these per arm, per each one of the joints, then you achieve steady walk engine. But the idea, the whole concept comes from here, that if you understand this, everything becomes much sweet and simpler. Then you can say, okay, now I can, like, what about my arm? I can also, my arm can follow the sign like this, right? But if you don't do that, your robot is like this. Okay, now part B finished. Now odometry, how we can achieve odometry now. So when you generate this, step starts from here. So we say this is support, flies, and get support again. Support means on the floor, and when flies on the air. So if I measure the distances of between the two supports per each one of the feet, then if I simply talk about moving forward, then I can calculate my odometry. Just the distances per each one of the legs, how much it is moving. That can be the odometry reading. Of course, for rotation, also you need to calculate it. How you can calculate it? You need to consider calculation of the rotation of the foot on the theta. Then you achieve odometry reading from humanoid robot. So this whole procedure, I also written on one of my publications that if you are interested in, you can read, you can see how kinematic chain and implementation of inverse kinematic works, how you can generate trajectory based on this simple trajectory, and how odometry can work on there. But here we've done like learning-based techniques, how we can learn with neural network that this output, of course, we have error because of its slippage and because of the uncertainty on the environment, and this contains a lot of error, and in different environments, because like on the tile and on the grass and different environments, this can be vary, and of course this can be trained by some neural networks to estimate the error and reduce the amount of error that we have. So if I want to summarize this chapter, the most important thing that we studied is velocity motion model, that we saw how we can calculate x prime, y prime, theta prime, new pose of robot based on old pose that we added the amount of velocity control commands that we have. And later we saw that, okay, this velocity control command is not enough because we have the error, and we added the error by replacing v and w by v hat and w hat, and we saw how we can, how each one, inside of each one of these is, and replace the equation, then add final error for final rotation, then we achieve the velocity motion model. So now, afterward, when we are talking about the control commands, in different algorithms that we're gonna see, so we can, instead of ut, feed the velocity reading or odometry reading based on what kind of robot we have and what we are going to do. Any question here or here?